So today's lecturer is Jerome Gauntlett from Imperial College London, and Jerome will be talking about equivariant localization in Supergravity.
Yeah, in my platform. I should have really helped. That's based on 3 papers that recently appeared. Yeah, Geneva, and my collaborator James Sparks, who was here last week. So the basic idea, or what these papers are about, is a new tool to extract physical observables, supersymmetric holography. So here's CFT from the gravity side, include gravity, and it'll be strictly classical gravity. And the key point is without solving Einstein. Disclaimer, you'll be learning in this talk, but no machine learning. There'll be numbers in this talk, but no number theory. This is purely a story about gravity and force. So people are looking for synergy with those other topics. Unfortunately, they won't find it here, and I won't be offended if they get up and need to discuss. Let's say I want synergy, but hopefully you'll get something, at least a flavor. So when I say physical observables, what am I thinking about? Well, let me just give you an overview of the kinds of questions we're interested in, and we can apply this methodology to it. So if you have a solution of E equals 10 or 11 supergravity, that's the form of an entropy space across M, and cost supersymmetry, meaning that it makes Killing spinor equations. We'll explain what that is if we haven't seen it later. And this is due to a D equals 1, D minus 1 supersymmetric probability. And of course, there's many things, if you have such a solution, so an explicit solution to the equation of the motion D equals 10 equals 11 supergravity, in principle, you can calculate everything about this field theory by doing gravitational calculations here. Now, I just told you I'm going to extract out observables without solving the Einstein's equation. So we don't expect to be able to get everything from here, but just some observables. And the observables I'm thinking about, for example, if D was 2m, there's things like central charges, which capture anomalies on this side, and also a measure the number of degree of freedom. We'll be able to calculate that from the gravity side without solving the equation. So things like central charges, free energies, on spheres, informal scaling dimensions of chiral primers. There's a few of these are the observable. Yes.
How important it is that you how important is
Well, it's critical. So we only understand CFT in the context of the string arrangement. Well, yeah, if you're going to do a lower dimensions, if you want to apply this in lower dimensions, then you better be sure that you can uplift to higher dimensions and then you get a solution. Otherwise,
why is that?
No, that's just the fact about CFT. Yeah. So this is the setting that we understand ADS-CFT in string theory. And there's ways of getting such solutions and discussing such solutions in clever ways by focusing on d-dimensional gravity, which is what you're getting at. But this is really the setting. So to the extent that how they apply in other contexts and what you want to do, there is things we can say, but I think this is the interesting. You're not okay.
No, I'm just curious about like, so that you can have a version ADS-CFT where n does not have a large part. Okay. So like,
Yeah, so everything I'm going to be doing is classical gravity and go with it. So
no, that m, the size of m.
yeah.
So if it had to scale with the size of ADS.
Right, so we don't have any examples of a nice hierarchy
Right, so
of scales.
How important it is that m is there.
That's a high bar. We don't have any examples whatsoever, but there's infinite numbers of these examples. And so that's what we're talking about. But we can talk about it. Yeah. Well, it's classical, but everything's classical. Right? You probably can do one and n corrections, and I won't be discussing it. I'm just going to
Could this actually you see it in the component.
Yes, let me just continue a little bit and then ask that question. So another application is the supersymmetric ADS black holes. So one of the big achievements of string theory is obtaining a state counting interpretation of the Bekenstein Hawking entropy for asymptotically flat black holes. And in the last 5, 6, 7, 8 years, people have started trying to do similar things in the context of ADS black holes that are asymptotically ADS. So here, the kinds of supergravity solutions you're looking for is a black hole that lives inside ADS-D. So it's asymptotically ADS-T%. So you can take one of these spaces and you can put a black hole in it, calculate its entropy. And then here you would like to do a state counting in the conformal field theory. And just let me say a few more words. The horizon, the black hole horizon, could have exotic topology. So in addition to a sphere, for example, SK, well, let me just go now in asymptotically ADS4, so it could be 2 spheres, it could be Riemann surfaces, they could be something else that I've been looking at over the last several years, things called spindles. Spindles are places topologically 2 sphere with conical singularities at the north pole. This topic is obviously intimately connected with the first one, and moreover, the near horizon geometry. So not the asymptotically and therefore ADS-D plus M, but the near horizon geometry looks like for a black hole ADS-2. Horizon across the internal space. A black string, it would be ADS3. So, in a sense, the these black holes. And logically, and the third kind of problem that we're interested in, we can apply these techniques to, is again related but slightly different flavor. So we take a supersymmetric conformal field theory and we put it on some Euclidean space. And preserve supersymmetry. And that's not a trivial thing to do. There's a lot known about when we can do this. And this will be dual to supersymmetric. Well, I mean, yeah, so that's the field theory side there. Where the gravity side would be, you would look for gravity solutions where you have a boundary, that's n. This is where you put the supersymmetric conformal field theory, And if you're interested in filling that in, this could be the boundary, some n tilde, this space here, then again, some internal space corresponding to defining the conformal field area. So if you look at the gravity solutions that asymptotically approach ADS cross M, but the boundary now has some arbitrary topology. And here, the kind of observable you'd like to calculate is that here the observable works these things, the observable here, and here you'd like to calculate the utility function, and that should be related to the petition function of the CFT on. Good. So those are the kinds of problems that we can apply this technology to. Let me just say a couple more words, which is connected with what Albrecht was saying. We know, first of all, this is, for people who don't know about this field, this is huge. What I've said, literally thousands of papers on that. So this is not just like small little corner. So I can't summarize all of this. But one general thing is a huge amount of progress being made on the conformal field theory side. For example, the central charge of conformal field theories can be calculated using something called A maximization. And there's a way of considering central charge as a function of some trial R-symmetry. And R-symmetry is a symmetry that rotates the killing stills, and you extremize this object. So that's kind of suggested there should be some extremization principle here. Black hole entropy, say counting the supersymmetric conformal field theory. Again, there's much to say here, but typically, or sometimes, in some contexts, you can look at an index, and there's conjectures about how to calculate those indices. And again, they satisfy some extremization principle, which suggests there's some sort of off-shell extremization kind of idea that you could apply here. And similarly, you can look at a complex locus of, you can look at complex saddles when you do these state counting computations, which suggests that there's actually, you should actually enlarge your domain of thinking about not just real solutions, but complex solutions. And there's again some extremization principles that you notice in the field theory that suggest that you have a black hole. And finally, in this context, from this conformal field theory point of view, typically what one's doing is a localization of the petition function in field theory. So I'm not going to be talking about that kind of localization. I'm going to talk about a much simpler kind of localization. But that localization in field theory is suggested there's some kind of localization going on the graph. So that's the motivation. And the big, so here, we're going to be looking at supergravity solutions with an R-symmetry. And all of these examples I've just been describing are. So that's what we're going to learn about. And we'll see that the new techniques will give us many exact results on the gravity side, which agree with the field theory side, but also go well beyond that. So let me just stop there and just see if there's any questions about what we're talking about. Yeah. Yeah. So this would be some, I mean, you take a field theory and then you say, well, I want to put on a sphere or a squash sphere. I have to use the Stuccio type things, see which background field does, which one symmetry. So you set up a field theory computation that way. And then you might be able to do a localization, turn it into a matrix model, evaluate that along the limit, blah, blah, blah. But the gravity side would then be finding such solutions. And finding these solutions in general, so there are many examples of specific solutions, but a general point is, in this program, it's impossible to calculate all the solutions explicitly. So we've learned through explicit examples how things are working, but to go beyond that, we need much more powerful techniques. And that's what I want to talk about. Okay, so yeah. Yeah, so I will I'll define that precisely later, but so it is a Killing spinor bilinear, and yes, and with the lead derivative of the Killing spinor with respect to that vector will be on zero. I don't know. Yeah, what we're doing is much simpler, and it should have been discovered 20 years ago. Yeah. Yes.
Should have discovered
it. Maybe I should have. Okay, so let me tell you about, in fact, the word localization appears everywhere in our field. And it evolved from papers by Busterman, Heckman, Atiyah, Witten. These people are Berline-Vergne-Atiyah-Bott back in the 80s. And things then were applied to field theory, path intervals, and so on. It became much more complicated and sophisticated. What I want to talk about is just the simple stuff. So I imagine, so this is just a little side map or a background. We have some even dimensional manifold. It has a Riemannian metric, and we have a Killing vector. And we also, crucially, have a polyform. Polyform is just the formal sum of forms, differential forms of different rank, such that the equivariant derivative of the polyform equals zero. So this is just the ordinary Hodge D, and this is a contraction of the form of the spinor. So it's psi mu only the mu over L. Like that. Okay.
and there are different around of that. Well,
No.
sorry, I meant in the first bullet point, and yes, you are.
So yeah, just new page. We're just doing even dimensional manifolds, and this yeah. And I'll come back. We'll come back to the connection.
So D pushes you up a rank and contraction pushes you down, and you sort of mix things because of the problem.
Exactly. So if we just spell this out, if we had the top form of even dimensional, the top form better be closed, but we need a 2n-1 form, which is given by contraction of psi with the 2n form. So we have 2n, 2n-2, all the way down to a 0. Exactly. And this operator is interesting because if you square it, you get d ixi plus ixi d, and that's also known as the lead derivative. The form language shows the lead derivative of that Killing vector is 55. So you have some operator, just like in Durham cohomology, d squared equals 0. You can define equivariant cohomology, which is defined as the forms that are closed, equivariantly closed, divided by forms that are exact with its derivative. So that's something you can define. If you have this structure, then you can define that. Yes. Yes. So, yes, exactly. I didn't say that, did I? So if we take 5 such that the lead derivative vanishes, then we can define that. So if the fixed point set of the Killing vector equals the empty set, that is just acts freely. So you have a an action of the Killing vector and it's just moving all the points on the manifold and doesn't mean anything invariant. You can define the manifold in one lower dimension And this equivariant cohomology equals Jerome Gauntlett. So you take your manifold, you divide out by all the action of the U1, you take the quotient space, and it just gives you the cohomology balance. That's the boring.
If you need Jerome cohomology of some quotient space.
Obviously. Yeah. Okay, but we're interested in fixed point set is not equal to cell. Is either points leading variant or higher or surfaces of higher dimension. And that means by the polyform, it means to choose the form of the dimension that you're integrating. Top form equals a sum over all the fixed point sets. They have codimension 2k. They have one df, which was pi to k. And then an integral over the fixed point sets. Form divided by this object here. Looks complicated, but actually it's not.
Is this actually what happens if F has singularity, the lower?
This formula is the fixed set, which would be points, three-dimensional, in fact, everything will be even dimensional without the one room, be points, dimension 2, 4.
Yeah, but I mean, if let's say the surface is that itself, we have to take.
Yeah, okay. So they can have orbifold singularities, and that's what that thing is. These epsilon I are weights of the action of the killing vector. I'll tell you what a weight is of the action of the killing vector. Phi here is the original polyform, but now we're integrating over F. And on the denominator, I have this product of 1 plus shown classes, and just think of these as two forms, like the field strength of a two-form field strength. So what do I mean? I mean, how do you integrate divided by a form? What this means is just expand this out, just do the expansion of 1 plus x minus x dot. Bring everything in the denominator up to the top, and then just pick out the forms which are the same dimension as that. Okay. So it's just a very, very compact notation. You can just expand it all out. That's a beautiful way of just summarizing. Is that an LI? That's a line marker, yeah. So I'm going to just unpack this a little further. So just this stage, that's the big formula, and that's exactly. Let's just do some examples to understand a bit more. So let's first look at isolated fixed points. So the statement there is rather simple. So this integral just becomes the sum over the fixed points of the product of these weights times the value of I naught on each of the fixed points. So let's do an example.
Sorry, so for the even dimension is not important, right?
In fact, it is. There's generalization of dimensions, but I won't be discussing it this talk. You have to do something different. But our application will be for even dimensions. So it's a good question. Not particularly, no. So let's look at S2, and let's work out the volume of S2 using this technology. So let's write down the metric of S2. And let's look at this killing vector. So some pictures. Killing vector is doing this. And you have two fixed points of the action at the north and south pole. And what about these weights? So let's look at the north and south pole. And if we blow that up, we get this picture. It's just rotating a little bit of R2 like that. And at the south pole, it's actually rotating a little bit of R2 in local coordinates that way. So the weight of the vector here is B, and the weight of the vector there is minus B. And if you want to be, you can make this more formal, but hopefully you're just getting the idea. Slightly more formally, if you calculated, so you've got a killing vector, you can define, we can use sometimes use notation, flat, because we lower the index to get a form. If you calculate the d of that, that's a 2 form, and then in these local coordinates, Cartesian coordinates, work out what this is, and at the north pole, you will find that it's this, and at the south pole, it's this. So this is a 2 form, so you skew diagonalize it in these Cartesian coordinates, and you would get those two results. So the main point, the weight here is epsilon is B, and here is minus B. Sorry?
You get the Euler.
No, we'll get the volume. So, I mean, you can do other things, but let's write now this polyform. Sorry, sometimes I think include the yeah. Okay, that is an equivariantly closed form. You can normally do that in your head, but it's just not right to see that. So we should be able to use this formula. There's only fixed points. So the integral of the top form is this. Is the volume. And now that's 2 pi beta cos theta on epsilon at the north pole, or beta cos theta on epsilon at the south pole. And because theta's changed sign at the 2 poles, and the epsilon's changed sign at the 2 poles, so you get 2 pi. Okay, so that's just, I mean, the point of that is not to display the power of this formula, but just simply that you can just see how it's working. So that's what these epsilon are, they're weights. And if we just had isolated fixed points, there's two normal directions for this point, but a fixed point in a higher dimensional space will have more normal directions. And so you're just going to get more of these weights. Yes. Yes, exactly. One big flat.
These cancels here, like you have one beat by 0 and 2. You really get one.
So B, so this thing,
Yeah.
the north pole.
Comparing to this equation to the right.
So 2 pi, and this n is just 1 here.
Oh, why is it 1?
Because this is the dimension of the space.
Ah, I see.
So the number of these epsilons is the number of normal directions the fixed points. So that's why this codimension, that's why this is organizing code. So if we just have fixed points, you can kind of see why, yeah, you're just going to get more epsilons the bigger your space is. And I'm not going to go in any more detail about these, except that if your fixed point is no longer a point, but it's a surface, then what you need to do is you look at all the normal directions, and there'll be weights associated with those normal directions. But this bundle also is fibered over the fixed point surface, and it can be written as a sum. It doesn't always have to be, but let's assume that that normal bundle is a sum of line bundles, and then that's where those churn classes come in. And finally, this, as I said before, if F is not a manifold but an orbifold, then you have to correct by some degree. B?
in this example.
Yes, these are the-
Is there any part or point where we would take special values or for the purposes of what?
So in this example, no, it's just the actual. I mean, if B is 0, of course, it's just a trivial vector. So in this case, it's just moving things around. But we're jumping way ahead. If I get there right at the end, you can apply this in a complex context, and you can actually use it to look at complex loci of black holes. Okay, jumping way ahead.
Okay, I'm still a little bit confused about it. I mean, normally, I mean, for the way that you apply in topological things, so you get it topological. It's not really dependent on the metric. But how you're saying, is this dependent on the metric really? Could you normalize it all?
Well, yeah. So I've totally. And what this has done is, yeah, it's integrated. It's integrated the top form.
Yeah.
That's what the problem is. But it's ultimately, going back to that picture, there's some sort of equivariant cohomology beyond all this. Okay, yeah, this is not a lecture about this. I want to apply this, but hopefully you've got a flavor. And this formula is the key formula. And just to emphasize, this was the starting point for logical string theory, localization of path intervals, Nikita's work on instant homologized spaces, all sorts of things. But this is a very, very, very simple thing by comparison. Good. So how are we going to try and use this? So we're going to consider now supersymmetric solutions of supergravity that have an R-symmetry. And this is actually the generic situation. So what do we mean by supersymmetric solutions of supergravity? So I'm going to be schematic here, but what I mean is that we have some Einstein's equations, supergravity theory. We want to solve those equations. There will be some flux or matter equations of motions. We need to solve those. That would just then say that you have a solution to the equations of motion of the supergravity theory. And we want to be supersymmetric. So we want to solve the Killing spinor equation. And the Killing spinor equation schematically is the covariant derivative of a spinor, and depending on exactly which case you're looking at, structurally some equations like this. So epsilon is a spinor, and the fluxes are going into gamma matrices in all sorts of complicated ways, but specified specifically by the supergravity theory, and you have solutions to it. So a supersymmetric solution is one that satisfies all of them.
So now we're solving. Away from that.
Yes, it is. So I'm just sort of backing up, going back to just maybe some people here don't know what I mean by this, but this is just the standard story. And this R-symmetry Killing vector, generically, you get something like. So if you calculate a spinor bilinear, then that turns out to be a Killing vector, and the Lie derivative of the spinor is non-zero, which means it's an R-symmetry. That's what we mean by R. Okay, so that's the kind of problem we're trying to solve, and Victoria said, well, we're eventually just going to go off shell, going to relax on it. But that's the problem we're trying to solve, and people have been solving this busily for many years in all sorts of different ways. So what I want to do is just illustrate by looking at an example. And if we get time, I'll give you some other examples that you can compare. So I'm going to look at 11-dimensional supergravity. And I want to look for solutions that are dual to any one formal field theories in full space-time. So ADS-CFT says I should be looking for solutions that have an ADS 5 factor. So this is the metric on some 6-dimensional internal space. This is the metric on an acidified space. This warp factor is a function of the coordinates on M6. So lambda is just defined on M6. So this metric has all the isometries of ADS5, which is associated with the conformal group on that side. So that's the most general kind of metric you want to consider. If you want to consider the most general one of these, which has a dual 11 dimension. And there's a fourth form in the X11 supergravity. There's a metric fourth form on fermions. And we again want this, we want to consider the most general thing that preserves all these isometries. So this should be a fourth form that just lives on N6. If the fourth form had any legs in these N instead of 5 space, we break this isometries of ADS5, and then it would no longer be due to form 2. So the data is a scalar, a metric, and a fourth form on N6. Say that again.
The same work pattern of the ADS5 and the template is not.
In fact, yeah, it's not important because I could absorb that and call that the S articulate squared. It's just, yeah, it's just one way of going. Good. And one more thing you need to do. So this is a supergravity solution, but you also need to make sure that G4 is an element of the fourth cohomology with integer values in M6. In plain language, we're doing flux quantization. So the integral of G4 on any 4 cycle in M6 better be an integer. So that's again part of the general framework for, I mean, we're not just doing supergravity, that's a bit of M theory there. That's what we need to do to get this. Okay, so I'm going to have to tell you some background before we get to the new part. In fact, I was thinking about this 20 years ago. That's the 20 years ago. And we tried to understand this geometry systematically. So what did we do then? And I'll tell you what we've been doing now. So this is the old story. Let's start with it. Let's take the Newton's 11 spinner and write it as a spinner on the ADS space times a spinner on M6. We can always do that. And then construct bilinears of the spinner. What do I mean by bilinears? I mean, we just consider things like this. So this is the spinner, right conjugate, and here I've got an anti-symmetric combination of the gamma matrix. So that's antisymmetric in our indices. So psi here is a rank R4. So I can construct those. I can also construct the charge conjugate spinners. Let's call them sigma. And these satisfy some algebraic identities. So if you just multiply them together, contract the indices, using Fiat's relationships with spinners, you can work out that they satisfy a lot of algebraic identities, and that can be analyzed systematically. And if we now say this is a Killing spinner, and I've written down the Killing spinner equation, but just schematically, it's that thing up there. So if I take a derivative of psi, I'll get a derivative of these two spinners. I can then substitute that equation in, And I'll get the derivative of psi related to the fluxes and bilinears in some very complicated way. So the big analysis you can do there. But the only point that I want to say is the Killing spinor equation imply that these forms satisfy some differential. So these satisfy some differential conditions mixed up with the fluxes in a complicated way. And I don't want to write them down because that's the only content that I want to communicate. And then you try and analyze this systematically. But before we go any further, one thing you find very quickly is this is the Killing vector. And just remind you that the differential condition of the Killing vector is this one. So you find that there's a Killing vector constructed from the bilinears, and these four-dimensional supersymmetric formal field elements, they have an R-symmetry. So it's actually fully expected that on the gravity side, there's something that is canonically constructed associated with the R-symmetry, and there it is. So we're not still done. You would then so that's, well, 1, 2, 3. If you now impose the flux equation of motion, so far, all I've done is construct some bilinears and impose the Killing spinor. If you impose flux equations of motion, then, and I mean the equation of motion for G, it turns out that implies the Einstein forms. Most of the Einstein equations are solved automatically by supersymmetry. You just need to impose this little extra piece. So back in 2004, with Martelli, Sparks, and Waldron, there's words that I'll just say now, which are not too important for the rest of the talk, but the Killing spinor defines something called a G structure. And you analyze that G structure. The G structure is the algebraic conditions. It has a particular torsion, so there are differential conditions. And you analyze that and try and make an equivalence between the G structures and on-shell CD solutions.
Sorry, just to make sure that I follow.
Yeah.
The curvature of the M6, what is that? Where do I see that the curvature of the M6 balance?
You don't in general. That will be the space of solution.
Oh, is it the set of 0.3 that satisfy that equation? That's the stuff where it comes from?
No. Well, so I mean, it'll be in the explicit solution space. What metrics here are allowed? That's no. So I mean, this form. I mean, this kind of language would be say, take one of these funny G structures defined by these bilinears, etc., impose that flux equation of motion, and once you've done that program, and you can take an ansatz, for example, to do that, that will pop in something that actually solves all the equations of motion. And then you can look at it and go, what is the M6 on a hierarchical scale?
Right.
What is topology? But that's the space of solution rather than the general. I mean, that's a specific solution rather than what that actually exists. I mean, there might be no solution. I mean, there might be the end. I mean, it's not. But
I think there's going to be composing your epsilon 11 into the equal spin on the ADS. Spin on M6, and then spin on the M6.
Yeah, I'm just.
yeah, maybe I feel you asking more complicated.
I just wanted to see at which point could I see that the Ricci theorem of the M6 was from similar size of the Ricci theorem.
Yeah, but the size part is that's the difference. That's to do with explicitly what your solution is. So it's that's you have to then find out.
I just wanted to see it and go how when you said number 3.
Yeah. I mean, number 3 comes about, if you like, the simplest way of playing it is the integrability condition. So you impose Killing spinor equation, and there's an integrability condition, and the integrability condition relates that to the Riemann tensor plus flux equation motion, and you sort of analyze that and say, oh, actually, I now see that the Einstein equation is correct. But this is just a way of repackaging the original question, which was that. That was the original question. If I'd given you that list, you wouldn't have said, oh, how do I see what the size of M6 is?
Oh, yeah.
And I've just told you this is another way of solving the Einstein equation, and it's an equivalent.
It's always like if I solve some of the Einstein equations, or if I solve all of the Einstein equations.
So this is all. So this is the old story, but that's equivalence. And so then there was, for many years, people applied this in many contexts, and then you start analyzing this, writing down ansatz, looking for particular instructions, finding lots of examples, etc. Okay, so that's the old story. And then the new story. These are important questions because it's a little bit subtle to see this off show. The first point is we somehow relax some of the information I just mentioned there, and we just look at these bilinears, which include the Killing vector. Plus some other things, which I'm not going to tell you what they are, but there's other forms that's included. And these ones are distinguished because they are the ones that are invariant under the Killing vector. These ones, because of the charge conjugate, this is roughly epsilon transpose epsilon. When you take the lead derivative, this is charge, and so the whole thing is charged. Whereas this is epsilon and epsilon star, so it cancels out. So we just consider a subset of the bilinears, crucial point number one. And then two, and this is a simple question. Let's look for some polyforms constructed from these Xi's and the G's, which are equivariantly closed. At this point, there's no guarantee there's any. If you're thinking about BVAB, it's a very natural thing to ask. And that was the key point. And then if there are, see if you can use BVAB, that formula up there, to calculate integrals of these parts. Good. So everything is Euclidean here because M6 is on this internal state. So many of the stuff will go across in the Lorentzian, but you obviously have to be careful. And I won't be doing that at all in the rest of the talk.
What's fixing the R charge of the Killing spinor?
That's a computation. In fact, it's either 1 or a half in this context, depending. I think it depends how you normalize your spinor, but it's fixed. Yeah, it's not a free variable. Okay, so that's what you start thinking about, and when you start thinking about that, the first thing is there are several of these phi's. The second thing is they compute the integrals of the phi's. They can compute physical observables. So I'll tell you in a second, but over M6, but it also can be when we do quantization over forces. In fact, I'll tell you in 2 seconds. And so, so prize 1, prize 2, and 3. And this hopefully covers the reason of telling you the old story a bit more. This is partially off shell. And it's partially off shell because the information that, so up there I told you an equivalence in that discussion. Here I'm saying, let's look at the implication of the Killing spinor equation, but not on all the binaries, just on the ones that are invariant. So some other information I'll just throw away. I won't need that information, and that's why I'm half the option.
So when you were listing the conditions in the new story, I guess naively one would have said that from a supergravity perspective, I'm trying to go to the offshore. You were trying to capture families of the n equal 1 superconformal of the theorem that you had in mind in the first place.
Yes.
You have isolated, you are definitely, there is always that side that captures the existence of R-symmetry, but you are not necessarily choosing how it is realized, because the choice of M6 has not been performed.
That's right.
Now, somehow, the part where I lose a little bit intuition, and I get that this is the big question that is coming, is that condition B is defined like homology, which is a well-defined mathematical structure without going on shell. Nothing forces you to do on shell. You only need tonic homology to be well-defined, you only need side of the vector with the honest. But the metric could be on shell.
Yes.
Now, is there a sense in which choosing different files picks up different theories or this?
No, so when I say it exists several five, that's a specific one. That's the problem. So let me just act thematically, let me put those up and then maybe keep asking the question. There's more than this, but these are the key ones to illustrate what I'm doing. So G was a core form on N6, and I'm not going to tell you. It just takes 5 minutes to say what it is, but that you can complete G with a 2 form and 0 form, and these 2 forms and 0 forms are constructed as the binomial. And that thing is equivariantly equivalent. So there's one involving the flux. There's another one, which is this warp factor, e to the 9 lambda, times the volume of the 6 manifold. And then there's a 4 form bilinear, 2 form bilinear. And actually this 0 form bilinear is this one cube. But that's what you go and see. I mean, it could have been that there was none. This obviously is making you think, well, this is going to help me do flux quantization. I want G, the integral of G on any 4 cycle to be an integer, but I can use BBAB and it'll relate. I'll do this. Now this one, you think, well, what's this? What's this stuff? Well, this, the integral of e to the 9 lambda volume 6 is not something random. It's equal to, if you work it out, put the factors in, I'm being slightly tilde, HG5, and this is the radius of the ADS space, and this is the effective 5-dimensional Newton's constant. Ignore that but the integral of this on M6 gives you the acentral charge of the dual field. So if someone gives you an explicit solution, you've solved all the equations of motion, the Killing equation, you would want to calculate this thing, and that would give you the acentral charge of the dual field.
But multiply to lambda.
Sorry, and 9. No, 9. Yeah, no, it's 9.
Oh, it's not.
The number's 9. I told you there's no number theory, but there's numbers. So in practice, I mean, what we did, we knew this fact. We knew that this was an assembly valve. And then we just said, oh, wouldn't it be nice if we could complete it? And we just played around. So it's a very good question. There must be something more systematic. And it just says, and that's an open question. And similarly with this one, once we found this, we said, well, can we do the box quantization? And that was just the trial and error. But there must be some organizing principle. So that's one of the open. So that's, yeah, is that slightly clear now? It's not like you choose these, they're just the theory is giving them.
But also stressing that whatever organizing principle maybe we have the choice of these different files given by different cohort.
Completely clear. Exactly. but these concretely exist, and yeah, and now it's equivariantly enclosed. So we can now use that, and we only have to input topological information about the manifold now to compute off-shell quantities about the field. So the spin of bilinears these size. That translates into different conditions on those signs. We're using that. But we're not using all the information on the killing spinner because I've thrown away the other bilinears. I'm just not the one that we're charged. So that's why I'm off shell.
Sometimes you use this just the theta, right?
Yes. I mean, from everything I want to do now is just involving these polygons.
Okay,
Yeah.
relative, like the theta, here, I don't need to talk about.
So to use that formula, we need a killing spinner. Sorry, killing spinner.
But like the side, can I do it as defined as the lead relative of the theta 0? I'm not have to talk about something will form made out of spinner.
Yes, you could, but I think that sort of obscures. I mean, ultimately, we're calculating these BPS observables, like this acentral charge. And the reason that, so I think it would be sort of wrong, but logically, yes. I mean, I just write down a set of forms. I say that they're invariant, they tell us automatic conditions. I can construct those and I'm good to go. So I can now effectively forget the spinner.
Yeah.
Yeah.
Okay. You don't need to know the thing, but you don't have to know what that is.
Exactly. Yeah. Exactly.
No, but I'm curious at which point you notice that point. I
Look, with this central charge, that's how I would look. And there's others. I'm not going to tell you them all, but this is one. Okay, so lambda was the warp factor. Remember, it was an ADS5 for M6, lambda was the function, and the 9 on the cube was just, it's just not the volume. It's slightly corrected volume. But it's, so you could have said, well, if in fact, you might have tried to say, can we construct an equivariant form of the volume? And you can't. Actually, when you can construct one with each of the 9 lambda volume, I see, and that's also and that's completely simple. That's not a coincidence. So I wanted to then I'll just give you a sketch of how to use this. Yeah. So yeah. So when I say use it, I now don't want to go and solve the Einstein equations and then calculate this thing and say, oh, there's a central charge in my dual field theory, and I have my supergravity solution. I'm going to calculate this just putting in some topological information. So I'll focus on some solutions that we have a lot of intuition about, which are wrapped fibrates. So let me just recall, if you take fibrates in 11 dimensions, they have a world volume R15. I can give you my bottle of wine. It's surrounded by a force field. You just think about that in 11 dimensions, and then that's the case. And if you take lots of these branes and you back react them, you get the ADS4 7 cross S4 solution of the equilibrium. That's dual to a n equals 0,2 field theory in 60. So what do I mean by wrap fibranes? Well, it means I want to think about fibranes that could be wrapping on some cycle in a Calabi-Yau manifold or something where I change the world volume to. So I take my fibranes and I wrap them on some two-dimensional surface. You can think about taking this field theory and putting it on this two-dimensional surface. if this theory is the supersymmetric conformal field theory, then there should be an ADS 5 plus M6 solution. But, and this is the point of doing the 5 branes, but the M6 has a particular topological structure. See this, and topologically, the 6-dimensional space will be a 4-sphere fibered over this 2-dimensional surface. So I haven't told you everything yet, but what I'm doing here is I want to use this formula and I'm telling you some topology which is naturally associated with these 5 branes. So we know that M6, not any M6 now, it has this particular vibration structure. And this is just an example. And there's a little bit more to it, but not much. So if sigma is a Riemann surface of genus G, people may have heard these words. The way in which supersymmetry is preserved is via something called a topological twist. And it doesn't really matter except to translate that as follows. The vibration that I just put down there is fixed by, you take 2 line bundles of degree P1 and P2. This is all, well, yeah, so I'm using it. So from a mathematical point of view, I could just forget all that intuition and just say, let's consider M6, which is length 4 pi sigma, and carry on. But since you're physicists, I'm doing it because we expect this to be associated with these things. Okay, so and the fiber, so this is 2 dimensions, and these are each 3-dimensional fibers, so 6-dimensional space. And P1 plus P2 has to be equal to minus the Euler character of the Riemann surface. So that's, I'll assume that, but that's 2 line bundles over a Riemann surface. It's not quite the same as this. So what I need to do is think about my S4 as embedded in 2 copies of the complex numbers plus the real numbers. So it's a 4th sphere in R5, but these 2 C's are associated with this topological condition. Okay. So that topological information, and now I do BBAB with these forms. I haven't told you yet what the Killing vector is. We're going to use BBAB. I assume that psi is d by d phi 1 plus d by d phi 2. The d by d phi 1 and d by d phi 2 are on a think of the 4 sphere embedded in R5. 1 phi 1 rotates this factor, 1 phi 1 rotates this factor, and there's no action there. So that's the generic Killing vector on the 4 sphere fiber. The fixed point set is the north and south poles of S4. You just wrote out, if you wrote out the metric in explicit coordinates on a 4 sphere, you convince yourself, but maybe you can convince yourself just by thinking about that picture there. But the fixed points of the north and south poles of S4, but S4 is fibered over sigma. So the fixed point set is now 2-dimensional, a copy of the Riemann surface at the north pole, and a copy of the Riemann surface at the south. So we want to use this formula appropriately. I'm not going to do this blow by blow, but I'm just trying to give you the flavor. There's no longer fixed points isolated fixed points, like in the example of the two-sphere way back at the beginning of the talk. It's now these two-dimensional surfaces that you carry up. We impose flux quantization, and there's only one Ford cycle. So you want to be being software normalizations, but you want the integral of G on the four-sphere fiber to the n, and then you can evaluate G on the four-sphere because G was a polyform using this formula, and this will give contribution on these two surfaces. You analyze that. And then you calculate the central charge, also using BVAB. And when you find that's a 9, 8, B1, B2, B1, P1. Oh, sorry, B1, P2 plus B2, P1. And one last thing, and it's a little subtly, but I have to say it. B1 plus B2 is 1. And that comes from analyzing the killing spin at the north and south poles. But let me not say anything more about that. The main point is this formula here. So just to reiterate, what I've done is I said, let's think about a particular M6 with a particular topology. Use the polyforms to evaluate, to do these intervals by BVAB. And there's some work here. It's not trivial, but it's not too complicated either. And you finally get this answer. And what's appearing here is B1 and B2, which was our choice of killing vector, rotating the four sphere. And B1 plus B2 is constrained from 1. And the other thing that appears here is N, which is the total flux of the total number of fibrates. And P1 and P2 was the topological information that the brains were wrapping that Riemann surface approach. So we derived this without solving the equations of motion.
Meaning this equation that we put on P was the kind of the
Yes.
and why you need.
So you need to just slightly more. I mean, I'll be quick there, but you could take a clavier, take a Riemann surface inside the clavier, wrap the fibrings on that Riemann surface, and then say I want the back reactor charge. So that first step, just probe brains wrapping the Riemann surface, that would give me that clavier. The normal bundle would. So yeah. Good. So yeah.
So you know the normal charge can be not.
Yes. 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 So we now extremize over the one independently B1 BI. And if you do that, this is the physical central charge of the group. So that was the off-shell part. We got a final answer, but it wasn't on-shell because we didn't impose everything. We got an off-shell answer, but if you extremize it, you get the on-shell. And this agrees now. So two things. There are explicit supergravity solutions that were constructed by R, Prof, correct. So they solve them, you write down them, you solve the killing spin equation, the Einstein equations, you make erosions regularly, you work very hard. That agrees precisely with this answer. So it's correct. Two, these people also looked at in field theory the A-extremization principle in the field. And this computation, it's a pure field theory computation. It's to do with analyzing anomalies in the conformal field theory, and you go through that exercise. If you pursue that, you get exactly this off-shell. So the off-shell BVAB localization result is agreeing with the off-shell supersymmetric conformal field theory.
So the extra parameters that file out
Yes, exactly. So in that case, B1 and B2 satisfying exactly the constraint is choosing exactly their. And in fact, it's almost exactly the same because the fibrane has an SO5 symmetry, and the R symmetry is you take the break down to U1 squared, and you choose a U1 that's one of those. So yeah, that's okay. Yeah, maybe press pause for question.
I mean, maybe this is a great practice to see what the rotations of the absence that we
Yes. So remember a force sphere bundle over the Riemann surface, they're rotating on the force sphere. So when you fix at the poles of the force sphere, you still have the base of the vibration. Exactly. So that's a basis. Right? Oh, sorry. Yeah, no. SO5, yes. No. So so I no because I wait.
Do you get a number or do you
So you're right. I definitely inputted that in the back of my mind, the full solution will not have SO5. So that's the extra killing vector you're imagining. You say, well, what about SO4? Or so various combinations.
not
Yes, you can use any one you like for that.
and all of them can do the
Yeah. You'll have to choose. Yeah, you have to choose your polyform. Associated
Yeah, no,
with-
but it makes it more complicated, but for the S2, any of the three filling
Yeah.
vectors would have to do the volume.
But in fact, all that will happen is that you just the one I wrote down, you just rotate it to another. So it's a bit trivial, I think. But here, yeah. So you could have, I could have said, let's look for S4 bundles over Riemann surfaces, and I want to consider my final solution has SO5 symmetry. And you may have been able to push this program throughout, I don't know, but we know for sure there's no solution to that. So I think the game is you want to impose, or you might be able to prove that some of them are obstructed. But this brings a very important point, which no one explicitly asked, which is it kind of seems magic what I did. I took, without solving any equations of motion, I've given you a rather complicated object. If you look at their solution, it's extracted from a rather complicated solution. It's a simple formula. So how is that possible? Well, a key point is this will be the answer if the solution exists. So nothing I said has mentioned existence at all. So if a supergravity solution exists, this procedure will give you the answer. So what would be nice, and this is way beyond where we are. But what we would like is someone to say, if these conditions are satisfied, then a solution must exist. So this is very much like Calabi-Yau. So no one has ever constructed a Calabi-Yau metric, ever. But there's tens of thousands of papers on Calabi-Yau, many things are calculated. So, and that's the reason there, is things are much better for footing because of Yau's. If you take, the manifold with particular topological properties, there will be a Calabi-Yau metric. Here we don't have Yau, but that's where I think this is going.
Well,
That,
no, this is clear.
oh no, absolutely, we don't know. Yeah, so the kind of conjecture I imagine would be in this sort of game. There's some other observables.
Then you need that the calculation.
No, so there's some other observables which I haven't discussed. So you can take on these solutions, if they existed, you could take a membrane and wrap a cycle, and it would correspond to a particular chiral primary. It would have a scale. So imagine you do this program, you calculate everything you possibly can. If this, for example, is negative, if this was negative on shell, you couldn't possibly be dual to it, so that would be obstructed. It might be some positivity conditions of this, these other things, and so on. That would be the way. That would be our projection. Exactly. Yes. Yeah. If the extremity doesn't exist, you're doomed. If this is negative, so there'll be. But that's purely conjecture. So, yeah.
So So this, I mean, also work with the non-repeated.
Yeah, so in principle, yes. But as you might know, when you have non-abelian symmetry, from the field theory side, we know that there's often not mixing in these symmetry. So there will be cases just from that intuition where on the gravity side you could do it, but you'll probably come across in some time. Actually, I can say it better. In some cases, when there is non-abelian symmetry, you can do it, and then you'll see that there's no mixing actually by doing the extremization problem. But it's less interesting because you know that that's sort of just coming on to the right. Okay, so the main point here is computing this, and it's not everything about supergravity, but computing this using this technology is much simpler than constructing the solution itself. These solutions that people constructed in the big scheme of things are very simple, and yeah, the program of constructing explicit solutions, saying, well, that's what I'm safe with, I'm happy with that. That's kind of doomed because the vast majority of solutions are not going to be able to write down in an explicit form. Again, think about Berline-Vergne-Atiyah-Bott geometry. But nevertheless, you can still do these computations using this more powerful technology, but only calculating very specific observables. Yeah. Well, let me see if there's more questions just then. Yeah. Right.
How would it look like? Everything, I think, and it's always coming at the interval.
Yeah. So there has been some papers where you can you modify the equations of motion, but the leading order your Killing spinor equation stays the same. So Nikolai-Bobov had some papers. So you can calculate the 1 n effects by correcting the solution by modifying at leading order by modifying the equations of motion, but not the Killing spinor equation. And so
I'm sorry, only for that's your main.
yeah, that's exactly the main ingredients. That will get modified. Yeah. Yeah, it's a good question, but but I think, but also, yeah, Atish Nabokar and Samir Mati similarly as Roxanne. So that's much more ambitious. And the Costello, yeah, and the Costello thing was, but in spirit, yes, in spirit, this would be like the leading order piece of such a bigger thing. As I said, this should have been discovered a long time ago, and then yeah. In the graph. Yeah.
So you know what configuration for supersymmetric. And then the question is like, what is the functional? But here, that's why in a very nice language, it was not, you know? That's part of the but from this box equation that you have, it looks very sort of like it seems like it's object, yeah, where you see that this thing is actually.
But I think, as I said, it's sort of like the generalization of this would be away from it's then applied to the full path integral. So I mean, your configuration space is not just a manifold with these geometric structures. It's on the space of all I think this could be pushed a little further to get one on NFX, but it hasn't been done. I mean, let me put it that way. But,
Very, very well.
right.
The analysis.
Exactly. And IDSAFT says they're ultimately the same, even though they may look very different. Okay, I think I wanted to say a few things, but there's just some more. We'll see how far we go. That's not easy. So what I just looked at, I just gave you an example of a calculation where I assume I had this vibration structure with a particular topological structure given by that Calabi-Yau condition. That's what we just did. You can also do the same thing when this is now a spindle. And a spindle, I told you briefly before, locally up here looks like R2 mod Zm plus. And locally down here looks like R2 Zm minus for the spindle. And you can do the same kind of thing, input a little bit more topological information about this vibration structure, but now you have to take into account these orbifolds. So this factor comes in. That's one point. And a second point is, unlike this case, this space doesn't have any isometries. The spindle does have an isometry. So now the Killing vector that you're looking at is a combination of all of these Killing vectors. So the mixing of the isometries of the part of the space you're wrapping your brains, and you can get a final off-shell answer A. So this is another case that the explicit supergravity solution is known, and you see it works. But yeah, at this point now I want to emphasize you can now, and we did, you can do many examples where there's no supergravity solution. So this is all just to work, see how all the mechanisms work, but now you can just take any M6 you like. And we did that in many cases. And jumping back further out, we've also looked at ADS3 plus M8 solutions of the conservative supergravity. And instead of ADS5 plus M6, these can now arise as the near horizon limit of black strings with a little bit of connection to black hole physics. And much of the formalism I just described can be applied in this context with a very similar flavor. And then the one other class has a slightly different flavor. So again, when I say we've done this, you construct all the polyforms, you do the, and then take examples to flux quantization, etc., get a central chart of that field theory. The other example we looked at was B equals 4 Euclidean supergravity. And this is actually, I almost started with this example, but decided not to. The action is just Einstein-Maxwell theory with field strength squared and a cosmological constant. But I now want to think about this in the context of theories with boundaries. So we have a given Hawking term on the boundary, and you also have some counter terms on the boundary to make this a well-defined setup. And in this four-dimensional language, this is some three-dimensional boundary. I'm imagining looking for solutions where we have this three-dimensional boundary with some topology, and then we fill it in the four-dimensional space with that boundary. And you can apply the localization now to this, and you can get an expression for the logarithm of the partition function of the field theory on space. I'm just going to write one final formula. This R-symmetry. In 4 dimensions, this can have fixed points. So the Killing vector would be epsilon 1 divided by phi1 plus epsilon 2 divided by 2. These Killing vectors in R4. Or these are sometimes called knots in the gravitational community. And you can also have fixed surfaces, sometimes called volts. And our 2-dimensional surfaces are fixed points. So the Killing vector would just have, would need to rotate one normal direction to it. And this on-shell action, with all this counter-term and boundary stuff and all these nonsense here, you can derive this formula. It's a very nice formula. The fixed point set is either bolts or knots. And you get this formula here. So the fixed points, the knots, literally a point in 4-dimensional space, there's 2 normal directions, 2 normal R2 directions. That's what these weights are. It's a fixed bolt. It's just a surface, and then there's 1 R2 normal direction. So there's just 1 weight, which actually blocks out this contribution. And the plus and minuses that appear here, it turns out that the chirality of the Killing spin on each of these nuts and bolts, and so you add them all up. So this is the full on-shell action, this 4-dimensional theory, with all the holographic renormalization taken into account. So this formula was actually first written down by Sparks, Gauntlett, and Atiyah-Bott. But there's a 60-page paper deriving this, and it's a very nice paper, but you can rederive this using all this new technology. So it's another illustration of this, and people who are aware of this kind of game know that you can now start using this to look at complex locus of black holes. And if anyone here has been looking at that, but that's one of the things you can do. Okay, so I think I'm going to stop now. So the main thing is it's a new way of computing objects of interest in supergravity solutions without constructing the solutions explicitly. Clearly, the things that you can compute, like the logarithm of these partition functions or central charges and so on, are something very robust in the supersymmetric sector of the theory. They're very protected, they're very central, etc., very canonical. There's what we've done so far is just case by case, see how these things are assembled. But there's clearly some bigger picture which canonically can organize that in a better way. And finally, I just wanted to mention that, yeah, that if I had a bit longer, I would have told you about this, that there is application specifically to black holes. And this via this formula is one way in which you can do it. Awesome.
Somewhere you look this, I don't know, this Facebook spindle.
Yeah.
So why don't you comment it before on G equals 0 and G equals 1? Also
so G equals 0 is the truth here. Yeah. Good. Yeah. If we'd done that, we could have added this in.
Yeah.
And it's exactly Yanis's question. You would find that everything would actually be independent. And the reason is for a two-sphere, there's actually the U1, this is what we're talking about, sits inside an SU2. And A maximization, non-abelian groups, non-abelian symmetry, those things. So it's a good, I mean, a better answer to Yanis's question would have been that. Let's do the two-sphere, put in that extra parameter, do this more general thing, and you would find actually that just drops out, and it would be the same formula I wrote down before. And the torus, yeah, what's the story of the torus? That was the answer with the torus. There is also an impact, but I'm not coming to that.
Like the shocks.
You could have,
You could have.
you could have.
It's either not interesting.
I'm just missing. Let me think about.
So what would you have said if I say do it on G2 and the manifold is G2? What would you have said?
So you need the isometric.
Yeah, but
Okay.
but that's not the question because you can do it because it doesn't depend on the general
Right.
until you have that.
You could do some.
And that's what we did south slope with the higher. It was a further. But if you would do that here, I mean, if you would take all the Riemann surfaces and sort of make it equivariant on the base,
I don't know. It's a good question. Yeah, can you do more than what they've done?
because it seems to be so independent topological that I mean the trick that the topological trick it works because it doesn't matter how you generate it in the sphere and then you decompose it into components so you have the action and the added power. So that in principle it works.
Yeah, possibly. Yeah. I mean, one thing I didn't kind of emphasize that in fact, this is a better example. When you start doing it, you impose the box quantization, work out the something, etc. The fact that you finally get an answer that just depends, in fact, agrees exactly with the field theory on exactly the same data is rather remarkable. Because it could have been, yes, you could do this localization, and now you've expressed, I mean, after all, it's an integral. So you've got one integral replaced with another integral on the sum. And it might have been just, you've got some information, but not that. But it somehow conspires every case to just give you everything's constrained the right way, you get exactly what you want. So there's definitely more to be understood. We don't have, that's not the way we see it.
I guess there's no clear way of saying precisely what is observed, right? Is that correct? Like, when we say precisely, I mean, which equation is not satisfied or what component of the equation is not satisfied?
No.
I mean,
So all those bilinears at the chart ones, we've just forgotten about them. And exactly what information do they have and how could you maybe add a little bit back in, and I'm not sure. But yeah. Good question. Yeah, and have we exhausted all the observables you can calculate? Right? This is, I don't know, maybe this is super conformal indices, maybe we can calculate that. And that might require a little bit extra